Hi everybody, this is Mr. Holsey. Today is November 1st. It's B-Day. Sorry, I'm unable to come into school today. I had this accident. My car is pretty bad looking. It's at the shop right now. Hopefully they'll be able to fix it up. It may or may not be totaled. I don't think it is. I don't think I'll have to buy a new car, but it does look pretty bad. My baby was in the car when it happened, but he's okay. He was smiling and laughing, and I'm okay too. Just probably a little bit sore tomorrow. So everyone's okay. I just had to get a sub because I'm stranded at home. So we'll go over this lesson 27 folder. This lesson 25 presentation. Fortunately, it's on Schoology. If you go down here to Unit 3, by the way, you can use these drop downs. That's very handy. Under assignments, this is activity 3.6. That's what we're going to work on. It's precision and accuracy. And then the presentations, this last one here, this is presentation 27. I haven't published 28 yet, but I will pretty soon. 27 is there. 27 precision and accuracy, activity 3.6 there. And this video, hopefully you found it in the videos folder. I don't have it up right now because I'm recording it. So find those couple of things so you can follow along pretty well. But we're starting this today. And hopefully you can look at this video to review this information as well. So if you're at school though, please put your phone up and sit in your assigned seat so it's easier for the sub. Like I said, open that assignment on Schoology, turn in that big packet to your tray like we have been in the past. So a couple of assignments, grades are due. So a lot of people are failing this 9 weeks because they are unable to get the quiz made up. That quiz happens to be 30% of your grade for this 9 weeks, for this grade check. So it's imperative that we get that checked up, or finished up. Notebook check is going to be next Thursday, Friday. So be on top of your notebooks. Stamps to 40, numbers to 100, and I've got a rubric almost published. And then we'll start a project shortly after that, or during when we do the notebook checks, we'll start the project, and the Unit 3 exam will be after that. Buy tape, please. Everybody needs to buy their own roll of tape. It's only $1.50, $1.60. And then I'm starting this new policy too, where if you have 3 missing assignments or more, I want you to come into detention with me. That's basically tutorials. Not a whole lot of punishment there, but if you don't show up to our scheduled time, then I will have to give you a further detention in the library, and I don't want to have to do that. So I just want to make sure you're caught up. I want to make sure you don't fall so far behind to where it's irreparable. Okay, so for today, we've got this presentation, this activity. I'm sorry, it should be 3.6. Yeah, 3.6, precision and accuracy. And I don't think you'll have enough time to finish all of it, but it's the rest of it, including the conclusion questions, will be due next class. Check your notebook as well. So here's the outline, 1 through 6. These concepts and skills are introduced by these slides, but if you want to review this, I've got this outline here for you. So the first concept is the empirical rule. When I'm presenting in class, I want you to draw 2 examples of normal distributions. If I'm doing this on Pear Deck, please draw it like that. Or if you're just watching this video, please pause this video and practice doing that in your notebook to make sure you've got it right. Okay, so normal distributions have to be bell-shaped like this. Some can be skinny. These are all 4 of these are normal distributions. They can be real skinny and tall. They can be real short and fat. They can be shifted left or right. But as long as you have a bell shape, that means you're normal. That means you have a normal distribution. Your data does. And that's really nice because with a normal distribution, aka one that's not, bimodal, or one that's not real skewed, or it could be skewed this other direction, one that's not real skewed or bimodal, or just is maybe uniform. If it's normal, you can do a lot of predictions with it. It's really great. Using standard deviations. That's another good use of the standard deviation. We said that standard deviation quantifies how far your data is from the mean on average, which is true. It's a measure of the spread of your data. It's a measure of the spread. But this empirical rule are these 3 percentages here. 1 standard deviation away from the mean. So if you had a mean of maybe 5 and your standard deviation was 3, then that would be 8 and 2, right? Because you subtract 1 standard deviation from the mean and add 1 standard deviation from the mean. So 2 to 8, that interval right there, 68% of your data is within that interval. And that's the red right here, this red interval. That's 68%. Then within the 2 standard deviations, that's the red and the green, that's 95% of your data is within those, between those 2 numbers. And then the third group, all 3 of those colors, blue, green, and red, 99.7, almost all of your data is in there. We've talked about outliers before. If you have outliers that's higher, that's more than 3 standard deviations away from the mean. It could be on either side. Those are outliers. That means you're further from the mean than 99.7% of your data. That's definitely an outlier. So I would definitely work on remembering these 3 numbers, 68%, 95%, and 99.7%. And maybe you can do this with your hands. 1 standard deviation, 68%. 2, it's going down the curve. 95%. And 3, whoosh, going basically on the flat part. 99.7. So 68, 95, 99.7. 68, 95, 99.7. See if you can come up with a jingle or a rhyme or a dumb joke or something for that to help you remember. Okay, here's an example. This is a pretty much normally distributed data set. It's a real data set of how many hotel rooms are occupied throughout the year. The mean is 125. I think it looks like out of 240 or so. Almost about half of the rooms are occupied most of the time. That's what that means, that on average, about half of the rooms are occupied. And then the standard deviation is 44. So if your mean is about here, 44 less and 44 more, that's 1 standard deviation away. So what is that? 125 plus 44, that would be 169. And then 125 minus 44, looks like that's 81. Correct me if I'm wrong. Between 81 and 169 hotel rooms, that's 68% of the days have that many hotel rooms occupied. Okay, if you do 2 of those, so 125 minus 88, which is 2 times the standard deviation, that gets you 37 down here, 37. And if you do 125 plus 88, I'm cheating, I'm using a calculator, that gets you 213. So that's 2 standard deviations away. So between 37 and 13, that's 2 standard deviations away. That's 95% of your data is in those 2. And then if you do the last, whatever that is, 3 standard deviations away, it's 99.7%. 99.7% of 365, 99.7% of 365 is 364 almost. So maybe there's 1 instance that's past that cutoff. So maybe I can go ahead and do that. 125 times 125 plus 44 times 3 standard deviations away. That's 257. It looks like it's way out here. And then, let's see, 257. And then 125 minus 44 times 3, that's -7. It's way out here. So unfortunately, in this case, all of your data ends up inside the 3 standard deviations. So we have no outliers. So it's 99.7 predicted. That's just predicted. It can be slightly different from that, but that's a prediction. Okay. Here's another example. If our mean is 0.08, standard deviation is 1.77. Again, you do that 0.8 plus 1.77, 0.08 minus 1.77, and that's the interval. That's the interval you have here with 68% predicted of your data. So I want you to give me a shot. What interval between your low number and your big number is that 68% of your data? So try to figure that out. Okay, we can look. Plus, like I said, plus 1.77 minus 1.77. So you take that mean, add 1.77 to it, you get 1.88. Subtract 1.7 to it, you get 1.69. So those are your values there. And then if you wanted to do plus 2 standard deviations, That's 1.77 times 2. 2 times the standard deviation. That's 95%. And then you can do that one more time for 99.7%. So here's another example. If you have a mean of this and a sample standard deviation of this, again, try to guess. Predict the range of travel distances within which 68% of cotton balls would fall, if this is your fling machine. Okay, and here's the math. Again, you subtract 1 standard deviation away, you add 1 standard deviation. So 68% of the launches will result in a travel distance between 1.59 feet and 3.26 feet. Again, you can do it for 95%. Here it is, twice the standard deviation on either side. Okay, the next skill is another notation for uncertainty. We've been doing the parenthesis notation, which I really like, but these notations are a little bit better in their own ways. Okay, so when you record measurements, you have to have 3 things. See if you can remember what they are. Here's the first one, value. You have to have a value for a measurement. A measurement also always has to have units and uncertainty. That's right, you were right. I'm guessing that you said the right thing. A measurement is the best estimate of a quantity. A measurement is useful if we can quantify the uncertainty. So here's another way to do the uncertainty. Let's get through a little bit of that. It's the plus minus notation. So with our measurement back here, 3.84, we would normally put that 4 in parentheses because that's the uncertainty. But you can also say it's 3.84 plus or minus 5/100ths of a centimeter. And that tells me that it could be 3.8 or 3.9, basically. 3.8 or 3.9, give or take a little bit. And that quantifies my uncertainty. That says, here's my resolution on that ruler, the centimeter ruler. I can tell within 5/100ths of a centimeter what my actual value is there. But I can't tell beyond that. When we put that parenthesis in there, that's saying that last digit is uncertain. It's the same thing here. We're saying this last digit has some wiggle room. So you can say plus or minus the 5/100ths of a centimeter. And then you can actually calculate that out. Add 5/100ths to the end or subtract 5/100ths from the beginning. And then you have this inequality here. So this is a plus minus notation. This is an inequality notation. Those are both very useful. The inequality, you normally see that with tolerances, and we'll do that once we get into manufacturing. And modeling and Inventor. And then this interval notation is really helpful when we quantify in statistics. You can see that whole interval there. Interval notation with the inequality. Okay, measured value is given on the left side, and the uncertainty is given after the plus minus sign. That delta sign, the triangle, means change in. X is your quantity, maybe the length of whatever you're measuring, plus delta x, that's the variable, and that delta x is equal to this 0.5, the little thing. Okay, that's a little change or variation. So we need to talk about types of errors. This is very helpful. Sources of errors in measurement. There are 2 main types, random errors and systematic errors. This would be a very good time to pause the video and read over this, make sure you understand it. Random errors are just what happens. Every instrument has random errors, and that's just an artifact of our universe with atoms bumping around to each other, random movement of those things, any kind of movement from your hand, maybe because of your blood, because we're wobbly creatures, anything that can be determined by repeated measurements. The systematic error is an offset, from the actual value. So that could be maybe when I shoot my gun to start a race, when I shoot the starting gun, and then somebody several meters away from me is timing it, they're not going to hit start on the timer until they hear the gun. There is a delay, though, in the sound from the gun to the timer, And so that little delay is always going to be there. That's a systematic error. It creates an offset. If you can calculate that offset, maybe you can account for that systematic error. That's a little tricky, but maybe you can do it. That's an artifact of your instrument there. Random error is an artifact of just randomness or any other kinds of errors in the universe. Okay, so uncertainty, we've got two kinds here. Single measurements, which is what we've been quantifying before, and repeated measurements. So that is included in taking a lot of samples. With a single measurement, we have the three notations that we've already talked about: parentheses, plus minus, and the compound inequality. And now we're talking about uncertainty in repeated measurements as well. And that's where we get into standard deviation and the spread of our data. That uncertainty is accounted for in there with this when we talk about the standard deviations. Pretty nice. So relating those to accuracy and precision. Try to think, is random error or is systematic error going to affect your accuracy? And then think about this, is random error or systematic error going to affect your precision? So I'll give you a second to think about that. Okay, yeah. The accuracy is how close your data is to the actual accepted value, or in this case, how close your bullets or arrows are to the bullseye. So this has low accuracy, this middle one, because all of those are clumped away from the center. So maybe there was a high wind that carried all of your data away. That would be a systematic error. That would be a systematic error. Then here, this is low precision. Maybe that's because you're a bad shot, or you know, you're not breathing well. It's going to be some random errors. Okay, that random errors affect precision, and then the systematic errors affect accuracy. Okay, here's another little quiz. A miscalibration in your gun sights is what type of error? Systematic or random? I'll give you a second for that. Okay, the miscalibration would cause this over here, all your bullets to be in the wrong spot if you aim it up properly. So that should be a systematic error. Okay, that should be a systematic error. That miscalibration causes a decrease in accuracy or precision. It should be a decrease in accuracy. You're going to be further away from the bullseye. Okay, and now I'll give you a second for this. Match each type of error with its type and what it affects. You got a lot of options there. Okay, maybe I'll come back to that later, or maybe I'll post the results to that. But I'm not going to go over all that. That's for you to get some more practice. Okay, so like we've said before, ideally a measurement device is both accurate and precise, and then those systematic errors are often due to calibration. Like we had in that example, the scale is going to be a systematic error that offsets your accuracy if it accidentally weighs itself. That's a miscalibration. You've got to calibrate your sights on your gun. You've got to calibrate all your instruments, even the calipers that will start. You have to calibrate, aka zero in the calipers. So all your tools, you got to start calibrating those. And precision is random error, like we said. So here's a skill. This is going into the activity. Let me pull that up. Okay, hopefully it's not too hard to flip back and forth, but we're going into the activity here. I would take a minute to stop and read this introduction. Okay, we talked about calibration and systematic uncertainty and all that. So jump down here to procedure. Number 1, 2 students are asked to measure the length of a credit card. The accepted value for the length of the credit card is 85.105 millimeters. I don't know how they get an accepted value. Maybe that's what their model should have printed their card at. Maybe that's what they wanted it to print at. And maybe they have these really very, very precise measurement tools that measure that length of the card. And so we're just correcting, or comparing rather, our measurement devices to that very precise one. Maybe that's how they get that accepted value. But a lot of times you won't have the accepted value. That's why this stuff is very powerful, because you can predict the true value. And we'll talk about that in a bit. So the accepted value is 85.105 millimeters. Student A uses a plastic ruler. Student B uses a precision tool called a micrometer. Or I don't know how to pronounce that actually, micrometer. And if you Google micrometer, it'll show just the unit. But this little tool here, it's really quite cool. You have this screw that when you turn the screw, it turns it's kind of like a caliper. It turns the jaws in closer and closer and closer very slowly. And then you can read the analog scale right there. So that's a pretty cool tool. We won't deal with that. We will just do the calipers. So one person has a ruler, one person has a micrometer. That's what I'm going to call it, micrometer, not micrometer, micrometer. To ensure good estimates of length, each student measures the length of the same card 4 times, and I'm sorry, that's more than 4, multiple times, and records the following measurements. So here's all the measurements. I want you to create a dot plot. Okay, so in your notebook, this is where all the answers to this activity are going to go. In your notebook, record a dot plot for these measurements, and also the ones in the activity. There should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So record a dot plot for all 10 of those. I should note the dot plot needs to be on the same line. So it looks like you're going to have some data over by 85.0, 85.1, 85.2, and then more data over by 85.3. So you're going to have to say all of them, maybe 85.1, 85.2, 85.3. You're going to have student B's data more over here, and student A's data spread out. Just a big hint. Okay, so if you've done that already, here's our number line, and we're plotting our data here. We've got 2 instances of 85.1. So that's where student A's go, and then we have a little bit more on the activity 2. But here's the first 4. And then for student B, we're going to use red. X is there. They're off a little bit to the left some, a little bit to the right some, but not very much compared to student A. Okay, so we have those 2. All finished, and yours should look similar to this, but with more data. So student A's data ranges from 85.0 to 85.2. Student B's data ranges from 85.298 to 85.301, and the accepted value is over there towards the left, 85.105. So B and C ask you to just tell me which student's data is more accurate. And B asks you about accuracy. C asks you to answer which student's data is more precise. Write those both in your notebook. Okay, which is more accurate, which is more precise. Student A is more accurate because student A's data actually includes the actual value. It's surrounding the actual value, not very precisely. Student B's is more precise because they're clumped together more closely. They have more repeatability. But student A's is more accurate. Student B's is more precise. And we'll quantify those in a second. So we need to talk about error for number D. First, find the mean. Yeah, the error is the measured value minus the accepted value. So we first find the mean of each set, and then subtract the accepted value from the mean of those sets. So find the mean of each set, and here's the mean. Sorry, 1 second. Here are the means from this data set. Your means will be a little bit different using the 10 data points. So add those to DI and DII. Okay, those are the means. Then you subtract the accepted value, which is the 85.105. That'll give you your error for A and your error for B. So those are those 2 errors. And yours, like I said, are going to be a little different from your DI and your DII because you have more data than I do on the slides. Okay, that's the error. Now for E, Find the sample standard deviation. Let me pull it up here. Find the sample standard deviation of each set of measurement data by hand or by using a graphing calculator or by using Excel or Google Sheets. And enter each value in the last row of the table. So like this, standard deviation. You need to add that into your notebook, the standard deviation page. Standard deviation calculations, rather. Okay, once you've found that, here I can show you what this standard deviation was. 0.08 and 0.0015. They should be kind of comparable to these, but again, a little bit different. Once you found those, we're going to move on to F in a second. We're going to use the empirical rule to talk about what standard deviation actually means. So the precision is related to, tell me, standard deviation or mean? Good answer. It's the standard deviation, yeah. The precision is related to standard deviation or spread. So I'm going to give you these four. Distributions along with their true values and the mean of that sample set. And I want you to tell me which ones have good precision, which ones have good accuracy, and then which ones have bad precision, bad accuracy. So I think one of them should have good accuracy, good precision, bad accuracy, bad precision, good accuracy, bad precision, and then the other way around. Bad accuracy, good precision. Okay, you've matched all those. Here they are. High accuracy, high precision. B is, let me just go back. High accuracy because the mean of the data set is close to the true value. High precision because there's a small standard deviation, tight spread. High precision. Over here, bad on both. Low accuracy because the mean is offset from a true value. Now remember, is that systematic or random error? And then also low precision. Is that systematic or random error? It spreads out your data set. High standard deviation. Over here, low accuracy, high precision. High accuracy, low precision. Okay, so you need to connect these three concepts. Accuracy slash precision. Mean slash standard deviation. Random error slash systematic error. Make sure you know which one goes with which. Okay, and then we're starting on E now. The best thing about all of this is that you can predict values. You can quantify precision due to random errors. I'm talking about the standard deviation. Okay, student A has a lower, student A, the blue one, has a higher standard deviation, so it has a lower precision due to more random errors, and because they're just using a ruler, a low precision tool. Student B, on the other hand, the red one, it has a high precision because it has a small standard deviation due to low number of random errors. Okay, and here's what we can do. We can predict to within a certain degree of confidence, where our true value is. So 68% confidence is within 1 standard deviation. 95% confidence is within 2 standard deviations. For now, we have an actual accepted value. So saying I can predict, or student B can predict that the actual accepted value is within 2 standard deviations of their mean with 95% confidence is a little bit tricky. It's a little tricky to understand. But if you did not have the accepted value, this is where you can start predicting it. For instance, what does it mean to have an 80% chance of rain? What does it mean to have an 80% chance of rain? Google it. It's pretty interesting. It's called probability of precipitation. I think that's what it's called. And it's really interesting how they calculate it. They use this concept called confidence, and they use the percentage of area that you're in. But they combine those two to predict whether or not it's actually going to rain. The true value of rain, wherever that is, they're using this to predict it within more and more confidence. So the further out you spread your interval, the more confidence you have that the true value is within your interval somewhere. Simply because you have more data points. If you have 68% of data points within one standard deviation, then it's 68% likely that the true value is going to be in there somewhere. If you have 95% of data points between two standard deviations, then it's 95% likely that the true value is going to be in there somewhere. Okay, so we're using those the empirical rule to predict where your true value is. But in this case, since we have the actual value, it's a little bit tricky. We're not really predicting it. We're just saying we know that it's in there with 68% confidence. I suppose since we already know this true value, we know that it's in a certain interval with 100% confidence, 100% confidence. But like I said, that's not really what statistics is used for. You really want to quantify how much confidence you have that the unknown true value is in your interval. Okay, so student A's data says that he's 95% confident that the true value is between 84.95 and 85.26 using the empirical rule that we talked about before. You take the mean of their sample and then you add and subtract two standard deviations. Okay, so use that to do Fi through Fiv, talk about the standard deviation, and talk about the confidence levels, the 68% confidence, 95% confidence. I don't think it mentions the 99.7% confidence. If you have time today during this class, please do number 2. That's with the piece of paper. It's on the table with a smiley face, and it says, "Measure me, please." Please do that, and then we can talk about, we can enter that data into the Google form. We can analyze it when I get back. And then do the conclusion questions for homework. All of this should be in your notebook. All the answers should be in your notebook. Please review this video as many times as you need to. Thank you so much. Have a good day.